Weather radar is one of the most critical and highly useful tools in modern meteorology, especially for short-term weather prediction and severe storm warnings. While computer models are better at predicting what will happen days in advance, weather radar is unparalleled at showing exactly what is happening right now and where it will be over next few hours. Here is a breakdown of why weather radar is so useful for predicting rain, along with a few of its inherent limitations. Radar provides high-resolution data on exactly where precipitation is located and the speed at which a storm is moving. By tracking this movement, meteorologists can make highly accurate short-term forecasts, often called nowcasts, down to the minute. Radars emit pulses of microwave energy that bounce off raindrops and return to the dish. By measuring the strength of the returning signal, that is reflectivity, the radar can estimate how heavy the rain is, differentiating between light showers, moderate rain, and torrential downpours. Modern radars use the Doppler effect to measure not just where the rain is, but how fast the raindrops are moving toward or away from the radar station. This velocity data allows meteorologists to detect wind shear and rotation inside a storm, which is why the primary way tornadoes are identified before they ever touch the ground. Modern dual polarization radars send out both horizontal and vertical energy pulses. This gives forecasters a 2D perspective of the size and shape of falling objects, allowing them to accurately distinguish between rain, snow, hail, or even non-weather objects like birds, insects, and airborne debris. Despite its immense power, weather radar relies on physical line of sight and microwave mechanics, meaning it has a few blind spots. Radar beams travel in straight lines, but the Earth curves. The further a storm is from the radar station, the higher the radar beam is looking in the atmosphere. This means radar can sometimes completely overshoot shallow, low-level rain clouds at long distances. The cone of silence. A radar dish cannot point straight up into the sky, which creates a cone-shaped blind spot directly above the radar station. Very heavy rain or large hail can absorb and scatter the radar beam so much that it essentially blocks the radar's vision. This can hide severe storms that are lurking directly behind the initial band of heavy rain. Very fine mist or light drizzle droplets are sometimes too small to reflect enough microwave energy back to the receiver, making them invisible to the radar despite it raining on the ground. Ultimately, while it cannot tell you if it will rain next Tuesday, weather radar is an indispensable tool for tracking active weather, predicting immediate rainfall impacts, and managing flood warnings. Weather radars typically operate in the microwave frequency range, most commonly between 2 GHz and 12 GHz. Meteorologists use different frequency bands depending on the specific purpose of the radar, balancing the need for long-range detection against the need for high-resolution detail. Here is a breakdown of the 3 primary frequency bands used for weather radar. S-band 2 to 4 GHz, wavelength around 10 cm. Primary use case and characteristics: long range up to 300 plus km. Used for large national networks like the US NextRad system. The longer wavelength easily penetrates heavy rain and hail without losing signal strength, that is low attenuation. However, it requires a massive antenna dish. C-band 4 to 8 GHz, wavelength around 5 cm, medium range up to 200 km, the standard choice for many national weather networks around the world. It offers a good compromise between antenna size, resolution and cost, though it is more susceptible to signal attenuation in very heavy rain than S-band. X-band 8 to 12 GHz, wavelength around 3 cm, short range up to 50 km, highly sensitive and used for localized gap filling, mobile storm chasing and airport wind shear detection. It provides incredibly high resolution data using a much smaller antenna, but the signal is quickly absorbed and blocked by heavy precipitation. The choice of frequency dictates a fundamental trade-off in radar physics. High frequencies, X-band, allow for much smaller portable antennas and provide highly detailed images of cloud structures, but the radar beam is easily blocked, that is attenuated by the very rain it is trying to measure. Low frequencies, S-band, require very large expensive antennas but can see through intense storms to detect weather further away.